Other questions? Any other questions? Okay. Okay, so 1.5, right? Let's stop smiling and get to work. Right, so 1.5 is basically just more review about functions, things that you've probably seen before, polynomials, functions, right, sort of like, I should say, combinations of functions, and parametric functions, which I think maybe you have not seen before. Maybe some of you may have not seen before. Okay, so again, just formalizing what you've seen, what you've learned in the past. Let's start off with a definition. So a function of the form p of x equals some constant plus some constant times x plus some other constant times x squared plus some other constant times x to the n, where the a are all real numbers, so the ai are all real numbers, and n is some natural number, is called a polynomial. Of degree n. Okay, where, let's say, the last one is not 0. Okay. So
what's that letter next to the A? What, the one after the thinking of
ai, a sub I. So let me write this. A sub I. So a sub I is in R for, maybe it's clear if I write it like this, where A0, A1, all these guys are just fixed numbers, and the last one is not 0. So just copy this down for a second, and then I'll say what I'll clarify it. Okay, so this is a typical mathematical phrasing, right? If somebody said to you, what's a polynomial, right? What's a polynomial? I probably should have asked you before, but it's never worked out in previous classes when I asked this question. So somebody says, what's a polynomial? Well, you might give some examples, right? You could say, 1 plus x squared is a polynomial, pi x plus minus x cubed is a polynomial. All these things over here are polynomials, right? And here's the general form. It's anything that is a sum of, that takes x to a sum of powers of x, right? Where those powers can be multiplied by some numbers, right? You have a constant plus some constant times x plus some constant times x squared plus blah 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 plus some constant times x to the n for some power, right? So all of these things that we could come up with over here fall into that form, right? They're all right. This one, right? It has a constant 0, right? This one is 0 plus pi x plus 0x squared plus minus 1x cubed, right? If I wanted to see that really this thing is in the right form, right? It's some constant plus some constant times x plus some constant times x squared plus some constant times x cubed, right? All these things fall into this form. So this is what a polynomial is, right? It's something like this, where these a sub i's, a0, a1 through an, are all constants, and this thing is a natural number, and the last one is non-zero, so that I can say it's of degree n, right? This condition is thrown in. This condition is thrown in so that it really is of degree n polynomial and not a degree n minus 1 polynomial or something. Is that clear? Does everyone see how to read this sort of thing? It's maybe a bit novel to you to see a polynomial expressed like this. But this is how people write mathematics. Okay. Any problems? Any please write? No. Okay. Definition number 2. If px naught equals 0, we say x naught is a root of the polynomial p. So p a polynomial. Let p be some polynomial. If p of x naught is 0, we call x naught a root, right? A root or a 0. Right. It's just where the polynomial gives the value 0. Okay, and here's a fact that you've probably seen before, and we're just going to present it as a fact. That is, I'm not going to explain why this happens, but you could say fact or superstition. I'm not going to tell you why it's true. So, in fact, at this point, it'd be very hard to explain to you why this happens. Every polynomial. Can be factored. So every polynomial, say with real coefficients, right? These guys, these a, right? These guys, as you know, are called the coefficients. Every polynomial with real coefficients can be factored into a product of polynomials of degree less than or equal to 2. Okay. And yeah, do you mind?
How do you find the degree again?
The degree is just the highest the highest power. The highest power. So we have this one, x minus x cubed. This is a polynomial of degree 3. Sarah.
On the left side, sorry, I can't read the last line.
This last line here?
Yeah.
Okay. If p of x naught equals 0, we say x naught is a root of p.
Okay.
Is a root of p or a 0 of p. Okay, so let me give you an example of what I mean by this statement. Here's a polynomial, x cubed plus 3x squared plus 7x plus 10. Here's a polynomial. Turns out that you can factor this into x plus 2 times x squared plus x plus 5. Okay. Every polynomial can be factored into a product of polynomials of degree less than or equal to 2. And that's what we've done here. We had a polynomial of degree 3. We broke it down into a product of polynomials, each of which is of degree less than or equal to 2. Okay. Yeah.
Can you break down the x squared plus x plus 5 into one?
Could you break can you break this down? Could you break this down further? Could you break this down further? The answer is yes and no. So if you allow complex numbers, then the answer is yes. So if this were a course and we're dealing with complex numbers, the statement would actually can be factored down into a product of polynomials of degree 1.
Okay.
Okay. If you allow complex numbers, then all polynomials break down into polynomials product of polynomials of degree 1. But in the reals, this one can't be broken down any further, right? Because you have to introduce complex numbers. Okay, so this is what's called these guys are all called irreducible. Irreducible, right? Meaning that they cannot be further factored. Okay, so I really should say a product of irreducible polynomials. Yes, Stefan?
Can you show me factored it?
Can you show how you factored it? Okay. Okay. So I will show you. I'm not going to show you the whole thing, but I'll show you a little. So I should say there is a surefire way of factoring cubics. Okay, just like you have, there is a surefire way of factoring of quadratic polynomials, the quadratic formula. Right? You can always factor them down into the complex numbers. There is also a surefire way of factoring cubics called Cardano's formulas, and it's very complicated. I don't know it myself. So there is a way of factoring cubics. There's a way of factoring quartics, degree 4 guys, and then I think the question is, can you? So the question is, can you do this for what about for quintics? Is there a formula for quintics, and so on and so forth? Right. This question is actually answered. It's impossible. There is no formula for quintics and above. So don't spend the rest of your life trying to find one, because it's actually proven to be impossible. Okay. Yeah. Anyway, I won't tell you the whole story about it. Okay. Anyway, so for this one, we're not going to. So I'm not going to tell you exactly how we do this, but so one by magic. This is not magic. By clever guessing, by assisted guessing, one can find that -2 is a root. Maybe some of you learned how to do this assisted guessing. It has to do with the factors of the last. The constant term and the factors of the first term. I don't know. We did this. I did this when I was a child, but then again, we didn't really. It was a long time ago. I don't think you guys do this anymore. Anyway, there's a way of making a guess as to certain roots. Okay, so you make this guess and you find out that -2 is a root. Okay, and then you're like, okay, I'd like to factor this. You use long division. Then use long division. You say, okay, I'd like to factor this. I know that one of the factors is going to be x plus 2, right? X minus the root. Right? X minus the root is going to be one of the factors. And so what's the other factor? Well, you use long division. So, okay, x squared gives me x cubed plus 2x squared. That gives me x squared plus 7x plus 10. So you get x squared plus 2x. You get 5x plus 10. And you get 5. Right? So this thing, right? Right? This thing divided by this gives you that with no remainder. Right? This thing divided by this thing divided by this gives you this with no remainder, and then you multiply it on both sides. Okay, so you can use long division to factor. If you can guess a root, then you can use long division to factor. You don't have to know this. You don't have to know this.
Oh, okay.
I mean, it's.
So you jump to it. You're like, oh, you know how to do this.
No. I just put it down because it's true, and don't worry. I mean, it's sort of a useful skill, and you may at some point in your math, in some, it may turn out that this comes in handy, but yeah. Kimaya, did you have a question? No. Okay. So here's a fact that we're going that will be useful. Every polynomial can be factored into irreducible polynomials. Just like every number can be factored into primes, right? Every polynomial can be factored into irreducible polynomials. It's the same sort of idea, exactly the same sort of idea. Okay. But we can't explain it to you until much later. Okay. Other things that other terms that you've probably heard before. We call f an even function if something happens, right? What do we mean by an even function? What's an even function? Symmetric about the y-axis, right? In other words, f of the graph would have to be symmetric, so f of x and f of negative x would always be the same. Right? For all x. And I'll introduce this notation. The upside down A means for all. We call f an odd function if what? Can anyone tell me using this sort of notation? Yeah, Mel?
When f of x equals negative
F of x equals negative f of negative x. So, right, the first one says that on the graph, whenever you take x and negative x, you have the same values, right? Whenever for every x and negative x, so it's symmetric about the y, right? So symmetric about the y-axis. And then the other one, for any x and negative x, you have to have the negative value, right? You'll get the negative value of the x, right? So f of x is equal to negative of f of negative x, right? So this is symmetric about the origin. The graph is symmetric about the origin. Okay. Can anyone give me some examples of somebody give me an example of an even function? X squared, right? X squared. This example, x squared will do, right? Whenever I take f of x and f of negative x, I get the same thing, right? F of negative x will be negative x quantity squared. That gives me x squared, right? And you might, for the other one, an example, Kelly?
x cubed.
X cubed, right? F of x is x cubed will do, right? Certainly f of negative x is negative x cubed, which is negative 1 cubed, x cubed, which is negative x cubed. Right, so you get negative f of x. Okay. So other examples? Can somebody give me a non-polynomial example? All right.
Y equals x.
Y equals x, that's actually still a polynomial.
Oh.
Right? Because f of x equals x, I mean, x is
Absolute value.
absolute value, great. So absolute value is an even function, right? Absolute value is an even function.
Why is y equals x a polynomial?
Right, polynomial, remember, is anything that looks like, anything that can be, anything that falls into this format, right? Well, f of x equals x is one such thing, right? It's just 0 plus 1x. 0 plus 1x.
Oh.
That's a polynomial. Right. Okay. Yeah, Victor. Okay. What about sine? What is sine? Or what about cosine? Those of you who remember.
Cosine is odd.
Cosine is even.
Even.
Cosine is the even one. Yeah. So cosine is even. Sine is an odd. We'll get to them later. Okay, let's go on. Okay, so just to give you an example, or maybe another example of one that doesn't obviously, right? You see why these things are called even and odd. These functions are called even and odd, right? It sure looks like the even functions have something to do with even powers in the polynomial. And it looks like the odd ones are the examples we came up with, excluding the absolute value, were ones that had odd powers in the polynomial. So you might wonder, what about cosine and sine? Right? You'll get to that later. So let me give you a hint that these can be expressed as infinite polynomials, where all the powers in cosine will be even, and all the powers in sine will be odd. Cosine, for example, turns out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus et cetera, et cetera. And then sine turns out to be something similar to that. Turns out to be x minus x cubed over 3 factorial plus x to the 5th factorial, et cetera, et cetera. Anyway, you won't see that until next semester, but not too long in the future. Okay, so enough about polynomials. Now let's talk about composing functions, or putting, maybe we'll call it generating new functions from old functions. So first off, just some notation. Functions and arithmetic. Okay, so this is nothing at all fancy. I'm just going to write down what I mean. So let's do an example. Once we do the example, the notation will be obvious. Let's let f of x be x squared minus 2, g of x be x plus 3. Okay. So if I write f plus g of x, what do I mean? What do you think that means? F plus g of x. It'll be sort of what you would obviously hope it would mean. Come back. You just add them, right? It'll be f of x plus g of x, right? That is x squared minus 2 plus x plus 3. Okay. So sort of the obvious notation. When I write the function f plus g, I mean the function that gives you f of x plus g of x. Okay. If I write f times g, x, what do I mean by that? Of course, I mean it gives you f of x times g of x. So minus 2 plus 3. Right. if I write f divided by g of x, you know what I mean. If I write 5f x, what do I mean? Just multiply by 5, so I mean 5 times f of x. Make 5 of f of x. So, just notation. Everyone all right? Any questions? Okay. More sophisticated. Composition of functions. Okay, composition of functions. Basically, what it is you have two functions, f and g, and you apply them in succession, right? You apply them in succession. So you take x and you apply f to it, and then you get f of x. You apply g to that, and you get g of f of x. Okay, and that function, that composed function, is denoted by g of f, g little circle f. The composition of g with f. Okay. So whenever we write g of f of x, we mean g of f of x. Okay. So for example, if I have f of x is x squared plus 1, and g of x is the square root of x, and I say, what's f of g of x? F of g of x. Then somebody tell me what, take 10 seconds and write down what that is. Okay, so what is it? What is it? What's f of g of x? X plus 1, right? It'll be x plus 1. Let me do it slowly. It'll be f of, g of x, f of g of x, right? So you take f squares whatever you feed it and adds on 1 to it. So you get this squared plus 1, let's just say x plus 1. Right? It'll be f of g of x. That's f of the square root of x. In other words, square root of x squared plus 1, x plus 1. Okay. A trick, sort of a quick trick question. What's the domain of this composition? What's the domain of this composition? So the domain is, what are all acceptable x that you can put into it? What kind of x will this function accept? Robert?
Real numbers.
All real numbers? So domain. Is it all of R? Other possibilities? Stefano?
Greater than or equal to 0.
R greater than or equal to 0? Okay. Because the answer is actually R greater than or equal to 0. Because the x has to go through the square root function first. Okay, and if you tried to feed in a negative number to it, then it would say, I can't give you an answer. Okay, in this course at least, it wouldn't give you an answer. Okay, so because to phrase it properly, the domain, so warning or remark, the domain of f composed with g is all points in the domain of g, the domain of g whose image lies in the domain of f. All points in the domain of g whose image lies in the domain of f. Okay. So we can't say it's the whole real line here, because the domain of g is not the whole real line, but just the non-negative numbers. Okay. Anyway, nothing, not that big a deal. Just just after that. Okay. Okay. So composition of functions. I think the last thing that any questions about composition? Is that
Wait, so I have a question about the image.
Yeah.
Since the image is the more specific part of the range, right? Or no, the domain.
Let me write it like this. All points x in the domain of g for which g of x lies in the domain of f. Maybe that makes it clear. This is what I mean by here's a point, and then here's its image under g. Right, it gets mapped to that thing. Okay. Last idea in this section. Standard question is f composed with g the same thing as g composed with f? No, right? Because if we looked at, for example, in this case, g of f of x would be what?
F of x inside of g.
Yeah, so g of f of x, so it would be the square root of x squared plus 1. Right? Which is quite different from f of g of x. Anyway, sure, okay. Last thing, parametric curves. Okay. So this is sort of an odd thing to give you guys, but we're going to do it. Given two functions, f and g, going from R to R. Okay. One can create a function gamma from R into R2, okay, where gamma of t is f of t, g of t. And this thing is called a parameterized curve, or parametric curve. It's called a parametric curve. Okay. So you have two functions, f and g, and you're going to use them as the x and y coordinates of your parametric curve. Okay. So let me give you an example. Here are two functions, f of t is t, g of t is t. Okay. And then you create your curve, gamma of t is going to be f of t, g of t. So So you create this parametric curve guy. Okay. And this thing is a curve in the plane. This thing is a curve in the plane. You see what it does. So you create this map. You create this guy gamma that goes from the real line into the plane. Okay, from the real line into the plane. And here for this one, for example, if we're at 0, what's gamma of 0? It'll be 0, 0. Right? Gamma of 0 is going to be 0, 0. Right? So it starts there. If we go to 1, we move up to 1, what happens? It goes to 1, 1, but along what path does it go? Sure, at time 1, right, it's going to end up at 1, 1. Here it's at 0, 0. At time 0, it's at 0, 0. After 1 second, it has moved to 1, 1. But what happened in between, out of curiosity? Well, anyway, let's think a little bit more. What about time -1? Where is it? -1, -1, right? You know, at time 1/2, where is it? 1/2, 1/2, right? And so you see that this thing is moving only along the line y equals x, right? So it's doing this, right? Right? It moves along this line. Okay. So this is the language for this is that this is a parameterization of the line y equals x. Let me do another example. Let's say that gamma of t is t comma t squared. T comma t squared. So let's think about that again. Right. At time 0, it's at 0, 0. Right. At time 1, where is it?
1,
1, 1. 1, 1. At time 2, where is it? 2, 4. 2, 4. Right. At time 3, where is it? 3, 9. Right. What about time -1? Negative 1, 1, right? We have -1, 1. At time -2, where is it? We have -2, comma 4, right? And you see what this guy is parametrizing. This is a parametrization of the parabola. Right? Okay. So this thing is the parametrization of the parabola. Leah, you have a question?
No.
Yeah? Okay. Okay. So anybody have a question? Okay, we'll do 2 more examples. Suppose I have something like this: t squared, t squared. Okay. Again, where are we at 0, 0? We're at time 0. At time 0, we're at 0, 0. Gave it away. At time 1, where are we? 1, 1. At time -1, where are we? We're at 1, 1. What is this parametrizing? Somebody said it? Absolute value. Great. Right. This will parameterize the graph of the absolute value function. Right. For negative numbers, right, we're going to get negative. We're going to get. Oh, wait a second. That's not right. That's not right. Sorry. We never get negative values. We never get negative x out of this. Okay? We never get negative x out of this. At negative, sorry. So at time 1, we go to 1, 1. At time -1, we're also at 1, 1. We're also at 1. Right. So I messed up. Yeah, Sarah.
So just that you're given like coordinates in terms of the x value and the t value, and then like that's how you define them.
Yeah. So you just plug in various t, and you get out the x and y from it. So you think of this as a time you put in, and then this is the position of the thing at that time.
Well, I guess I'm just like confused. What's the difference between that and like the normal solution?
Let me give one more example quickly. If I had something like this, cosine t, sine t. Where are we at time 0? We're at cosine 0, sine 0. Where is that? It's actually 1, 0. So 1, 0. So at time 0, we're here. What about at time pi over 2? Where are we? We'll get cosine pi over 2, sine pi over 2, which is 0, 1. What about at time, so this is at time 0, this is at time pi over 2. What about time pi? Where are we? Negative 1, 0, right? This is at time pi. At time 3 pi over 2, we're here. And as time, you see what goes on. As time goes forwards, we start here and we zoom around the circle counterclockwise. Okay. And as time goes backwards, we zoom around the circle counterclockwise. Oh, I'm sorry, that was counterclockwise, this is clockwise. Okay. So this is not exactly the same thing as like a function and its graph. Okay. It's really a dot that is walking around in the plane at particular times. Okay.